Okay, so some details on optimization to just say a little bit about. The first is this issue of local versus global extreme values. So let's just go right into that, and I'll show you what I mean here. So let's say we have a function that looks like that. Okay, that's our f of x. And we can tell just kind of by looking at it that we've got a max here, a min there, another local max here, a local min there. Okay, so if we went through the process from the last lesson and found the critical points by finding those that satisfy the first order conditions, the points that have a first derivative equal to 0, that would be our 4 points there. We would find these 4 local extreme values here. Okay. X1, X2, X3, and X4 are local mins and local maxes. Okay, local is being used in sort of the obvious sense here. X1 is not the highest value that the function takes everywhere, but it's the highest in its little neighborhood. And it is, so it's a local mountain. It's the top of a local hill. X4 is not the lowest point that the function takes overall. There's a lower local minimum over here at x2, but more importantly, the function here, if we extended it, let's really extend it here, is shooting off to negative infinity and off to positive infinity. So if we went through our process, find the critical points and classify them, we would find the local minima and the local maxima. In this case, the function has no global max or min, okay? As this kind of wiggly part of the function that's close to the y-axis, but then after the minimum at x4, the function looks like it's just heading off towards infinity there. Since we found all the critical points, we know that it's not going to turn around and start decreasing again, because we would have found that isn't at the critical point. And similarly, as x is heading toward negative infinity, the function is also heading toward negative infinity. And again, we know it's just going to keep on doing that because if it wasn't, it was going to turn around and we'd have another critical point here. Generally, I think really the point I want to make about a function like this is if we had to work with something like this, we would. We just sort of have to be interested in the behavior below the smallest critical point and above the biggest critical point to see what's happening above it if we were interested in whether there was a global minimum or a global maximum. And it's all doable. It doesn't arise that often, okay? More often we have enough wiggle room in choosing functions to represent our ideas that we don't have to work with something as out there as this very wiggly function. And generally, mathematical models are most useful when they're as simple as possible. So stay away from fanciness, especially gratuitous fanciness. It makes the math harder and doesn't really help. Okay, so point one, it's an issue. Most of the time, it's an avoidable issue. If you start reading, especially if you're reading, game theory, formal theory, you'll see people assuming that the functions that they're working with are globally concave and globally convex. And a big reason for doing that is to capture most of what you want to say about the real world process without having to deal with all these local extreme values that are not global extreme values. Okay, if we have a function that is globally concave and it has a local maximum, that local maximum will be a global maximum. Okay, so let me just say that. That's the function that is globally concave, local max will be a global max, but there won't necessarily be one if there is one. A function can be globally concave, like log is globally concave, but it doesn't have a maximum. It doesn't have a local maximum value. Flip side of that, a function that is globally convex, if it has a local minimum, it will be global minimum. Okay, so those global second derivative properties, if we're interested in global extreme values, super duper helpful. All right, so that's loose end number 1. Loose end number 2 has to do with inflection points. So what am I talking about here? What inflection points are places where the second derivative changes sign. Okay. Second derivative changes sign. Okay, so the function might go from being concave to convex or convex to concave. We're not generally all that interested in inflection points, but where they can come up is when we're looking for extreme values, they can satisfy the first order conditions, okay? Okay, so inflection points can occur where the first derivative equals 0. And kind of a classic example of that is f of x equals x cubed. So f prime of x equals 0 at x equals 0. And you can just see from the graph that it's not a max, it's not a min. There the function is globally increasing. It has no maximum or minimum value. But right here at x equals 0, it goes from being concave function to a convex function. Convex, increasing first derivative, positive second derivative. Okay. So at this inflection point here, the second derivative changes from being negative to positive. As I said, generally we're not interested in finding inflection points for their own sake, but we are interested in identifying them because they can show up when we're looking for maxima or minima. Okay, so something, you have a critical point, maybe it's a max, maybe it's a min, maybe it's neither one. It could be an inflection point. I should say you can also have inflection points where the first derivative is not equal to 0. So the first derivative being equal to 0 is necessary for a local minimum or a local maximum. It can happen at an inflection point, but it's not necessary. Okay. That's really all there is to say about inflection points. Another thing you might be wondering about, it's got a long-winded title, but a picture that you might be wondering about. I'm going to get at the issue of differentiable versus non-differentiable functions. That's a mouthful. Differentiable means you can take its derivative. And really what that means is that the first derivative exists, that difference quotient has a well-defined limit. Okay, so that as delta x is getting smaller and smaller, the slopes of those secant lines are approaching unique tangent line. Okay, an example of kind of the famous example of a function where that fails, and it fails at kind of the place you're most interested in, is the absolute value function. Okay. So f of x equals the absolute value of x. So for that function, when x is in the positive range, it's just the same as 45-degree line. The y value is the same as the x value. When x, the argument, is less than 0, then y equals negative x. Absolute value has a point right here where it is not differentiable. And in general, functions that have these kind of pointy corners are not differentiable at that point. You can take the derivative of the absolute value function any place other than 0. They're just lines, either the line of y equals x on this range and y equals negative x on that range. But at that one point where x equals 0, you can't take its derivative. And an easy way to just sort of see that graphically is to think about all the different tangent lines. Balance off a bunch of different lines there. Okay. We have too many tangent lines. So when we're saying that the slope of the tangent line should be the limit of the difference quotient, what we're looking for that limit is we're looking for like one number that the rise of a run is getting closer and closer to as delta x is getting smaller and smaller. We're not looking for a whole bunch of numbers. When you have more than one number, you would say the limit of y x does not exist. So the reason why I'm bringing this up right now is I hope I haven't gone so far as to say for like all functions, all local maxima and minima can be found through the first order condition. I probably sounded pretty close to that in the previous lesson, which is like why I'm kind of slapping the asterisk on it now. That's mostly true because mostly when we are implicitly thinking about differential functions. It's also something that you will find yourself reading. You'll see people assuming that their functions are twice continuously differentiable. And what they mean is that the first and second derivatives, they exist, okay, so that we don't have these pointy corner issues to deal with, and they're smooth functions. Why people are saying that is what they're basically saying is, I'm making the assumptions that I need to in my model about how the world works so that I can use calculus to analyze things. If you don't have differentiable functions, you're going to have to figure out some other way to understand. Calculus is not really going to help you with it. Yeah, okay. No other point I think I want to make about non-differentiable functions. Final point. This is about corner solutions. Okay, so one way to think about corner solutions is, what if you're trying to optimize a function? What if you're trying to find the maximum of a function, and it's got the wrong kind of second derivative for you? Okay, you really want to maximize a function, but it is globally convex. Okay, what are you going to do there? Two answers on that. If you are trying to find the maximum value over the entire domain, like the entire real line of a globally convex function, hang it up. There isn't one. Okay, so globally convex function, something like squared. There's no global maximum. It just keeps getting bigger and bigger as x heads off toward either positive or negative infinity. Okay. No global max over the entire domain. Okay. So that just kind of bad news. It is what it is, no maximum. But sometimes when we have kind of a restricted domain, okay, like we are finding the value of x that is within a specific kind of finite set, okay, so maximize on constrained interval. So let's take an example here. There's a concave function over the entire domain. We know there's no maximum, but let's say that we are looking at just this set, okay? On, bring back my inadvertently erased axis and function here. Okay. So over the interval x0, x1, f of x, here is my function, does have a maximum. X equals x1. So that's generally going to be true. If you're trying to find the maximum value over an interval where the function is convex on the entire interval, you're not going to find a critical point that will be a maximum. You might find a minimum there, but that's not what you want. If you really know that you're looking for a maximum, it is going to occur at one of the corners. Okay, why we call these corners, it's kind of sort of get what they're saying. You might call them edges or boundaries, something like that. But corner solution is what they're called. And what you do is you just, the simplest way to find the maximum on this kind of interval is just to compare the values at the lower end and the higher end there. Okay, and that is sort of tying back to in the last unit what we said about second derivatives. When you have a function that is convex, so that you are having increasing marginal returns over the increasing range there. I was describing those kind of functions as sort of the more you get, the more you want, the more you have, the more you need. These functions sound like the reason why people can spend all their money on heroin. It can be kind of destabilizing. This is the corner solutions show you how that happens. That if your preferences really are like this, you will either do best by completely staying out. That's not true in this case, or by going in all the way. And I don't want to make it sound like we never think that we're looking for maxima over convex functions over these small intervals. So these, I can come up with these real world scenarios where you might think behavior is that way. But again, those kinds of solutions, corner solutions, are not going to show up through the first order condition, second order condition process. Okay. So FOC, SOC, just as we sometimes say first order conditions, FOC, to denote the condition that the first derivative has to equal 0. If we're classifying those critical points with a second derivative, people call them SOCs sometimes. That process, or even more broadly, the process of finding critical points and classifying them, that will find interior extreme values. Corner extreme values must be checked separately. Okay. Yeah, so if we were taking the derivative of this function, we would find a place where it equals 0. That would be a minimum, though. And if we're interested in the maxima, we'd have to just check the two boundary conditions. Okay, so that's kind of a whirlwind tour of some of the more advanced topics in optimization. The Sitzer Aaron Hammond, the EMEA book, goes into some of these in a lot more detail in chapter 8 and in quite a bit more detail in the rest of the book. So if you're interested in pursuing optimization techniques more, or reviewing more advanced optimization techniques that you might have run into before, the later chapters of that book are terrific for that. That's all we're going to do here in Math Camp. As far as Unit 6 is concerned, we got one more lesson with just a few examples. So I'll see you then.